pushover analysis and time history analysis. I'll discuss in depth the various options available in MIDAS Civil for these type of analysis, and I will also tell you about some of the limitations that MIDAS Civil has or some of the considerations that user must follow for the analysis. So this is the overview of seismic analysis or the dynamic analysis in MIDAS Civil. For the elastic seismic analysis, you can do the equivalent force method analysis or the response spectrum analysis. For the dynamic and for the material nonlinear behavior, you can do either the pushover analysis or the nonlinear time history analysis. So let's get started with the eigenvalue analysis. The procedure of eigenvalue analysis is, I have simplified it here. First, we need to specify the structure mass. Then we will define the eigenvalue analysis control, and after performing the analysis, we can see the eigenvalue analysis results. In MIDAS Civil, the structure mass can be defined in one of the following ways. We can either define the lumped mass or the consistent mass, and any one of them can be used for either eigenvalue analysis or pushover or time history analysis. The lumped mass in MIDAS Civil can be defined when you define the structure type. If you go to model structure type, you can realize that you can either select the lumped mass and you can either select the consistent mass. If you select the lumped mass, then MIDAS Civil converts the self-weight into masses and it lumps the masses of an element at its nodes. So if an element is made up of two nodes, the mass of the element will be divided between the two nodes for the lumped case. And if you specify the nodal masses, you can specify the mass to the nodes, or you can convert the loads to masses, because sometimes we do not model the barriers, but they are there in the structure in reality, and when the earthquake comes, the force applied by the earthquake, which is equal to the mass of the structure multiplied by the acceleration, is dependent on the barriers too, and hence you can convert the barrier load or other loads to masses to perform the eigenvalue analysis. Here, when we convert the self-weight into masses, the rotational mass is not considered automatically by MIDAS Civil. So if you want your structure to have rotational mass, then you must define the rotational mass in the nodal masses dialog box, as you can see here. Also, if you see the option here, there is an option known as consider off-diagonal masses. In the lumped mass, we have an option known as consider off-diagonal masses. Let me tell you now what is the function of this option. Let's say this is an element here and I have defined the offset to be center top. So that implies the element offset is at the center top and these are the nodes which shows the element. If we check on the consider off-diagonal masses, then the mass will be lumped at the centroid of the element. But if we do not check on this option, then the mass will be lumped at the node and not at the centroid. So if you want the program to consider the mass at the centroid, which is the reality, then you must check on this option. Also, if we select the option in the structure type as consistent mass, we can either convert the self-weight into masses, or we can also convert the loads to masses, and the fundamental remains the same. The lumped mass will be different from the consistent mass. Let me take you to the program now and show you where you can do this. So if I go to model, structure type, I can either convert the mass to lumped mass and I can consider the off-diagonal masses after checking on this option, or I can consider the consistent mass by checking on this option. Here in this structure, I will use the lumped mass and I will consider the off-diagonal masses. Now I will apply the barrier load as the mass. For that, I will go to Model, Masses, Load to Masses, and the additional load that I have specified here represents the barrier load, and I have converted the barrier load to the masses in the X, Y, and the Z direction. One thing the users must understand here is that if they have defined the self-weight under a load case as I have defined here, I have defined the self-weight under the load case named self-weight, and if I convert the self-weight to mass by going into the option load to masses, as in this, if I do this and I click on OK, and in the structure type I do not convert the self-weight into masses, then the program doesn't consider the self-weight into masses. So in a way, if I convert the self-weight into masses for the self-weight in the load to mass dialog box, then it is wrong and the program doesn't consider it. So the only loads that can be converted into masses are nodal loads, element beam loads, pressure loads, and the flow load, as you can see here. Now I have defined the load that I want to define as the mass, and I have converted the self-weight into masses by this structure type option. Now I have to perform the eigenvalue analysis. Eigenvalue analysis is very simple in MIDAS Civil. You don't have to define too many options. You just have to go to the eigenvalue analysis control. After you go to the eigenvalue analysis control dialog box, you will see certain options such as the eigenvectors and the Ritz vectors. Under the option of eigenvector, you can either select subspace iteration and or Langos. The difference in the analysis result of subspace iteration and Langos is not too high, but when can we use Langos or when can we use subspace iteration depends on the structure type. Ideally, if the structure is too complex, it has a lot of elements, then we go for the Langos type. But if the structure is simple, then we go for subspace iteration time. And for your information, Langos reduces the analysis time. But if you try to check the results from subspace iteration or Langos and you try to match them for a simple structure, the results will be identical. Also, there is another option known as Ritz vectors. Ritz vectors are used when the initial modes of the eigenvalue analysis have much dominant role. Here you can specify the load case which you want to use for the eigenvalue analysis, and you can specify the load case, also the number of generations. So here I have specified several load cases and I have specified the count which would be used for the generation of the Ritz vectors. Also, when we are dealing with the cable bridges such as cable stayed bridges or the suspension bridges, then for the determination of the cable stiffness, we need to know the pretension force in the cable. If we are doing a construction stage analysis, then we can convert the final stage cable forces as the pretension forces in the post CS mode, which would be used for the determination of stiffness of the cables for the eigenvalue analysis. So if I go to the construction stage analysis control data, I can see an option named initial force control, and if I check on this option, then MIDAS Civil will determine the stiffness of the cable as per the pretension in the cable in the previous stage. So let's see how we can implement that in the program. So if I go to analysis, construction stage analysis control, I have checked on the option, that is, I want to convert the final stage member forces to the initial forces for post CS, because I am dealing with a cable state bridge here, and the cables need to have a stiffness, and since the stiffness of the cable depend on the pretension force, so I need to specify that option. Now I go to the eigenvalue analysis control, and I will select the Lancos as my method of eigenvalue analysis, and I will specify the number of frequencies. And now I am ready to run the analysis. So after I run the analysis, I can see several results pertaining to the eigenvalue analysis. Let me talk about the results first, and then we will see the results in the program itself. So the results that the user can expect from MIDAS Civil for the eigenvalue analysis are the natural mode shapes, the natural periods, modal participation factors, and the effective modal mass. For your information, when we do the eigenvalue analysis in MIDAS Civil, the mode shapes, the periods are determined for the structure which doesn't have any damping. So while determining the eigenvalue analysis results, the structure is considered to be undamped. Now let's see the analysis results in MIDAS Civil. If I go to results, vibration mode shapes, I can generate the mode shapes for more than one mode together. As you can see here, this is the shape of the mode for mode 4, mode 5, mode 6, and mode 7. Also, I can see the individual mode shape for an individual mode. As you can see here, this is the mode shape for the first mode. Also, on the right hand side, I can see the modal participation factor, and this implies, I can see here, the percentage is in DZ is the maximum, which implies that the principal mode deflects in the Z direction. Also, I can generate the tabular result. If I click on this option, I can see the frequency and the period for the individual modes, and I can see the modal participation masses, modal participation factor, and the eigenvectors accordingly. So this represents the eigenvalue analysis results in MIDAS Civil. And let me tell you at this point of time, if you want to do the response spectrum analysis or the time series analysis, then eigenvalue analysis is must. So that was all about the eigenvalue analysis, the several options available for eigenvalue analysis. Now let's talk about the response spectrum analysis. So let's first talk about the purpose of the response spectrum analysis. Response spectrum analysis is a dynamic analysis of a structure subjected to earthquake excitation using the response spectrum. So basically, it combines the response spectrum with the eigenvalue mode shape, and it gives you what could be the probable behavior of the structure for the earthquake loading. So this is how the response spectrum analysis is performed in MIDAS Civil. First, we perform the eigenvalue analysis. We determine the mode shapes, the frequency, period, modal direction factor, and the effective modal mass and ratio. Then we combine it with the spectrum function, and then the program performs the response spectrum analysis as desired. So this is the procedure to perform the response spectrum analysis in MIDAS Civil. It's a three-step process. First, we define the response spectrum functions. Then we define the response spectrum load cases. And finally, we can see the results pertaining to response spectrum analysis. So now let's talk about the response spectrum functions. We can define the response spectrum functions if you go to load, response spectrum analysis, and response spectrum analysis functions. This is the window, the dialog box that appears if I go to this path. And here you can realize that there is a design spectrum. The design spectrum contained in MIDAS Civil has the database of many codes that has been implemented. Let me take you to the program and show you how we can do it. So if I go to the design spectrum, I can see the design spectrum for certain codes as IBC, Eurocode, Korean code, Taiwanese code, Indian code, and Japanese code all together. Also, you can define the spectrum function either as normalized acceleration or the simple acceleration, the velocity or the displacement. So if you specify the response spectrum function in any one of these, which varies with the period, then you can find the acceleration for a pertaining period, and MIDAS Civil will apply that force to that particular mode shape, and the response spectrum analysis results are produced. Now the second step is to define the response spectrum load cases. The response spectrum load cases can be specified in load, response spectrum analysis, response spectrum load cases. Here, this is the window that appears when you select the response spectrum load cases. The excitation angle here represents the angle with the x-axis. So if the direction of the response spectrum is xy, then if I specify 0 here, then the force will be applied in the x direction, and if I specify the excitation angle to be 90 degrees, then the force will be applied perpendicular to the x-axis, that is the global y-axis. Also, if you select the option here, modal combination control, MIDAS Civil has implemented all the modal combination types that engineers typically use for combining the response spectrum analysis results. So if I use the SRSS, which is the abbreviated form of square root of sum of the squares, basically the response of different modes is squared and the under root is taken for the final response. Similarly, the complete quadratic combination, that is a CQC method, it combines the spectral results using structural damping and a weighted ratio of relative frequencies. The act of combination removes the sign of the result, thus leaving only a magnitude for the final answer. But here, if you check on this option, then you can add signs to the result. So if a user wants to have not only the magnitude but the sign of the result, then he can check on this option. Also the absolute sum, which is the the summation of the absolute magnitude of the responses can be used, or the linear sum can also be used. Let me talk about the add signs to the results function now. Here we can specify whether to restore the signs deleted during the mode combination and specify the restoration method. The restoration method can be along the major mode direction. Since we don't know what results are positive and what results are negative, we can specify the positive direction either along the major node, or we can specify the positive or the negative direction along the absolute maximum value. Also, we can select the mode shapes. We can select the mode shapes for the modal combination. If you want to exclude some of the modes from the response spectrum analysis, then the modes that appear here can be used. Also, if you keep going down, you'll realize that there is an option known as correction by damping ratio. The correction by damping ratio is used when the user has specified only one design spectrum. If the user has specified only one design spectrum which pertains to single damping ratio, then this equation is used to modify the value of the acceleration for that particular mode. For example, if the user has specified the spectral acceleration versus period graph for the damping ratio equal to 5%, then MIDAS Civil has only one value, and if the damping ratio for a particular mode is 5%, then that value will be automatically taken. But what if the damping ratio is not equal to 5%? Then this equation is used to determine the spectral acceleration. If you don't want MIDAS Civil to use this equation and you want to define certain set of spectral data as per different damping ratio, then you can also define several number of spectral design spectrums, and you can specify the interpolation procedure. So if you specify the linear interpolation procedure, then the linear interpolation between the several damping ratios will be used, and if you apply the logarithm interpolation, then logarithm interpolation method will be used for the determination of spectral acceleration. Also, the user can apply the several damping methods that are available in MIDAS Civil. The several damping methods that are available are modal. The first is modal. The user can define the damping ratio for each mode, and the modal response will be calculated based on the user defined damping ratios. This becomes handy when the user has the knowledge about the damping ratios for several modes. Typically, the users specify the same damping ratio for all the modes, and this option is suited for that purpose. Also, the second is mass and stiffness proportional. Here the damping coefficients are computed for mass and stiffness according to this equation. I will show you how later in the program, and the strain energy damping method can also be used. Here the program will use the strain energy for the determination of the damping ratio for individual modes. So before moving on to the pushover analysis, let's try to perform the response spectrum analysis on this model. So first I'll go to load, and I will define the response spectrum functions. So let's say I define the response spectrum function as the design spectrum of Eurocode 8, and here the user can specify the damping ratio. If you want to use your own user defined values, then you can specify the damping ratio here, and I click on OK. Again, I will specify one more design spectrum. Let's say this time I specified the UBC 1997 design spectrum, and the damping ratio I've kept the same. Now the second step is to define the response spectrum load cases. Here I will define the response spectrum in the X direction with the excitation angle of 0, which means that the direction will be the global X axis. I will select the Eurocode elastic design spectrum. The modal combination, as you can see here, I will use CQC, and I have selected all the modes which I want to use for the response spectrum analysis. I can also unselect any one of them. I will apply the damping method. As I told you before, I can apply the damping ratio for all modes, or I can specify the damping ratio for individual modes like this. If I use the mass and stiffness proportional, I can either specify the direct specification, that is, I can specify the value of A0 and A1, or I can specify the calculation from modal damping. Since we have two variables in the equation here, since we have two variables in this equation, we need two different periods or two different frequencies to determine the values of these two. We can do that automatically in the program by specifying either the period. Let's say the period of mode 1 is 5 and mode 2 is 10, and the damping ratio for mode 1 is 0.05 and mode 2 is 0.08. So as you can see here, MIDAS Civil has automatically calculated the values of the constants. If you specify the strain energy proportional, then the screen becomes blank. The reason is, when we specify the strain energy proportional, then we have to specify that in the group damping. So if I go to model properties, I can see here the group damping from strain energy proportional, and here I can specify the various data required. The obvious question arises on what method should be used. The strain energy method is used when we have different materials in the construction. So let's say we have steel combined with the concrete, then we would go for a strain energy proportional method. I will use the correction by damping ratio since I am using only one design spectrum, and I will click on add. And I will define one more in the Y direction with the excitation angle of 90 degrees. And since I have already done the eigenvalue analysis for this bridge, so I don't need to define it again. And now I am ready to run the analysis. So in this model, I have already defined the response spectrum functions and the load cases. And now I can see the results. If I want to see the response spectrum results in the Y direction, then I'll select the response spectrum that I applied in the Y direction, and I can see the bending movements. And if I want to specify for X direction, I will select the X direction response spectrum. Not only this, the user can see the deformed shapes also. Sometimes it is desired that the code advises that we have to use certain percentage of the X direction and certain percentage of the y direction. We can do that by combining, we can create a combination in which we will specify the x direction to have a factor of 1 and y direction to have a factor of 0.3. It means that in the x direction we are taking the 100% contribution, and for the y direction we are taking 30% contribution. So we can check out the results for different combinations. As you can see here, it combines the results of response spectrum X and response spectrum Y. Also the stresses or the truss forces, which are the cable forces, can be seen. So that was about the response spectrum analysis in MIDAS Civil. Now let's talk about the pushover analysis and the various features available in MIDAS Civil for the pushover analysis. The pushover analysis procedure in MIDAS Civil is straightforward. We need to define the pushover global control. Then we need to define the several load cases for the pushover analysis. Then we need to define the hinge properties. Then we will assign those hinges to certain elements, and then we will see the results. So the first step is to define the pushover global control, and moving on to the load cases, we'll define the hinge properties, we'll assign the hinge properties, and we'll move on to the results. So now let's talk about the pushover global control in detail. As you can see here, the various options are available. If the user wants to include the construction stage analysis results to perform the pushover analysis, then he can select the import static analysis or construction stage analysis results option in the pushover global control. And the user can select what load case will be provided what factor to be used as an initial force for the pushover analysis. What does this initial force means? Let's say we have a structure which has a self-weight. So before the earthquake appears, the self-weight will already be acting on the structure. So for the simulation of that, we need to specify the self-weight as the initial weight. Also, we can specify the stiffness reduction ratio for the skeleton curve. The skeleton curve is the hinge. So as you can see here, this is the trilinear hinge and this is the bilinear hinge for the pushover analysis in MIDAS Civil. Now let's talk about the pushover load cases. If I go to design pushover analysis, pushover load cases, I can see several options which are available which the user can specify for the pushover analysis. Here the user can consider the P delta effect, which is very important for the pushover analysis, because if we have vertical loads and the structure deflects in the positive x or the y direction, then there is an additional moment at the base of the structure, and to use that moment for the pushover analysis, the user can check on this option. As I was talking about the initial load, the user can select whether the initial load would be used for the output of the results or not. That is, if you want the initial forces to have their contribution in the reactions, then you can check on this option, the cumulative reaction by initial forces. And if you want the same in the displacement, then you can check on this option. The increment method can be chosen as load control or the displacement control. The load control specifies that beyond a certain force, the pushover analysis stops, while the displacement controls means that the hinges have certain deflection, and beyond that maximum deflection, the program stops to do the pushover analysis. So here, as you can see, I have selected the displacement control and I selected a master node which will have the maximum displacement in the dx direction to be 30 centimeters. But the question arises, what kind of load increment method must be used? The user can either go for load control or the displacement control, but generally when the hinges are bilinear or trilinear type, then the user must go for load control, and for the displacement control, when the hinges are femur type, then the user can go for displacement control. Also, there are certain load patterns which the user can select from. The load pattern can be selected, the one out of the mode shape, modal and the uniform acceleration as defined in the codes. And the mode specifies at what mode do you want to apply the pushover analysis. The mode is very important to specify, because if you have specified the direction of maximum deflection in the x, global x direction, then the mode must have the deflection in the x direction. And preferably that mode must be selected which has the maximum participation factor in the x direction. Now let's talk about the pushover hinge properties available in MIDAS Civil. As you can see here, in MIDAS Civil you can specify the material for the hinges. It can either be a reinforced concrete or a SRC, steel reinforced concrete structure, or it can be either steel or SRC filled. So the user has the option to select either the encased or the filled SRC type of material. Also, the user can specify the hinge in terms of moment rotation or the moment curvature or the moment curvature distributed. So MIDAS Civil provides a variety of options to the users for specifying the hinges for the pushover analysis. Secondly, the interaction type can be either none or the PM interaction can be taken into account. So if you are assigning the hinges to the beam elements, then the interaction type must be none, and if you are specifying the hinge properties to the columns, then the interaction type must be the PMM interaction. One thing that the user must understand while specifying the interaction type as PMM is that we should always specify the properties for the FX component, because when we are talking about the column, the major forces are the axial forces, and dependent on those axial forces is the PM interaction curve. Now let's go back to the program and see how we can do the pushover analysis in MIDAS Civil. So I have done a pushover analysis for a simple pier here. I have defined the pushover global control, and I have used the initial force as the self-weight of the pier and the self-weight of the deck over the pier. I have also specified the load cases, and as you can see here, I am trying to perform the pushover analysis in the X direction, and I have used the displacement control, and the maximum displacement that I have specified is 30 centimeters. Now the third step is to assign the hinges. For that, I'll first define the hinges, and here, since I'm defining the hinges for the column, I have used the PMM interaction, and I will check on the FX. Once you check on the FX, you can see the yield surface properties for the PM interaction curve, and if you want to change the values, you can have the input method as user. Then you can change the values for the moment in the Y direction, or you can change the values for the moment in the Z direction. And after performing the analysis, I need to perform the pushover analysis. So my pushover analysis has been performed. So basically the analysis of pushover is a two-step process. First you need to analyze the whole structure, and then you will analyze the pushover from the task pane, or you can analyze the pushover from here. Now let's check the pushover curve generated by MIDAS Civil. So this is a simple pushover curve, base shear versus the monitor displacement, and as you can see here, the program stops after 30 centimeters of the maximum displacement. You can see the pushover curve for shear coefficient versus displacement, shear versus drift, or the base shear versus displacement. You can also determine the performance point as per FEMA. You can change the design elastic spectrum, and if you change the design elastic spectrum, you can determine the performance point for that design spectrum. User can also see the yield step table, which shows when the yielding of the member has taken place. So as you can see here, the yielding for the moment in the Y direction and the Z direction has taken place at the fourth step, and the second yield has never taken place. Also, the user can check the yield status in the graphical format for different steps, as you can see here. So basically, if I specify more displacement as the maximum displacement, then I can obtain more failures as per the hinge definition. So as you can see here, the hinge status changes. Also, the yield step changes as I change the maximum displacement, because now the program divides the same displacement into 30 steps. So this is all about the pushover analysis in MIDAS Civil. Now let's go back to the presentation and talk about the time history analysis features in MIDAS Civil. In MIDAS Civil, the user can perform the time history analysis in the following two manners. The user can either perform the boundary nonlinear time history analysis, or the user can perform the inelastic time history analysis. Apart from the inelastic time history analysis, the user can also perform the elastic time history analysis. Throughout the course of time history analysis presentation and models, I'll show you the various methods available for the time history analysis. MIDAS Civil provides a wide variety of options that the user can use for the time history analysis, and we'll discuss them one by one. So this is the basis of time history analysis. The nonlinear model of the structure is combined with the seismic input, and the response is generated. And this is the fundamental theory behind the linear and the nonlinear time history analysis, the equations that are considered here. So this is the procedure of the time history analysis by MIDAS Civil. I have wrongly written it as to be the procedure of eigenvalue analysis. I'm sorry for that. So first we need to define the properties of nonlinear links. So if you are doing the nonlinear boundary time history analysis, then you need to define the nonlinear links. Then you input the several nonlinear links, assign them to the structure, and then you specify the time history load case, the time forcing function, the ground acceleration, and then perform the time history analysis and then check the results. So let's talk about the general link available in MIDAS Civil for performing the boundary nonlinear time history analysis. So as you can see, if we go to the model, boundaries, general link properties, I have an option to select the element or the force. If you select force, you can select several dampers and the base isolators available in MIDAS Civil. So primarily the application type can be element or it can be either force. When you specify the element, you can specify the inelastic hinge properties as it is. But if you specify the force, then you can specify the lead rubber bearing isolator, or you can specify the friction pendulum isolator and many others. The base isolators, summarizing the base isolators provided by MIDAS Civil. As you can see here, MIDAS Civil provides the viscoelastic dampers, the gap, hook, hysteresis system, base rubber isolator, friction pendulum isolator. So the first step was defining the general link properties, and the second step includes assigning the general link properties. So let me open a model and I show you how we can do that. So this is a model that I have previously prepared for boundary nonlinear analysis, but the method is simple. So for telling you more about the method, let me open an unmodeled structure. So this is the model that I will be using for time history analysis, and as you can see here, I have provided several supports to the structure as this, and I have made two nodes as this position. So basically I have applied a rigid link between the structure node and this node, and I have provided a support to this node. So this is the rigid link and this is the structure at the top of it, and I haven't provided any connection between these two. So basically my intention is to provide a lead rubber bearing isolator between these two nodes. So first I go to model properties. I'll define the general link properties, and I name it lead rubber bearing, and I can specify the weight of the bearing which can be used for the analysis, and I'll specify the stiffness in the X direction, in the Y direction, and in the Z direction. I can also specify the damping coefficient here, and I can specify the nonlinear properties as well. So as you can see here, I can specify several parameters for nonlinear properties. And I can specify the nonlinear properties in the Z direction too. Here I am using random values just to demonstrate how we can do that. And I have defined one lead rubber bearing isolator. Now I want to assign this isolator to my structure. For that, I will go to general link here, and I can select the property and I can assign it between two nodes. So if I click on this, I have assigned a general link to my structure. After assigning the general link to all these type of supports, I will specify the time history analysis data. So the first step is to define the time history load case. So I can specify a time history load case as, I'll give it a name, and I will select the analysis type as nonlinear. I can use the one of the analysis method as modal, direct integration, or static. So let's talk about the time history load case data first. So as you can see here, we can either go for linear analysis type or non-linear analysis type, and I'll demonstrate both of them in my webinar. I can choose any of the analysis method as modal and direct integration, and the time history type can be either transient or periodic. For the structures like bridges, we always go for the transient time history analysis. The second important option in the time history load case is the order in sequential loading, and we can make it subsequent to any load. So that means before the earthquake happens, there could be several other forces acting on the bridges as the barrier load and the self-weight of the bridges. So the time history analysis can be made subsequent to those forces. So in a way, it is equivalent to the initial forces in the pushover analysis. The damping method can be one of the modal, element mass and stiffness proportional, or the strain energy proportional, and all those rules which are applied to the response spectrum analysis are applied here. But the fundamental difference between the response spectrum analysis, element mass and stiffness proportional is, in response spectrum analysis you cannot specify different elements, different stiffness, but in the time history analysis you can do that. And how you can do that? Let me show you. So if I go to model, properties, group damping, element mass and stiffness proportional, I can specify different stiffness or a type of material, and I can specify several damping ratios. Now the next thing in line is to define the earthquake loading. We can define the earthquake loading using the time history time forcing function, and in MIDAS Civil we have implemented certain past happened earthquakes which the user can directly select, and he can see the behavior of the bridge under those earthquakes. The third step is to define the ground acceleration. Basically, ground acceleration means we are combining the time history load case to the earthquake. So here I will specify a time history load case name, and I will attach it with the earthquake. And the important thing to note here is the angle of horizontal ground acceleration. We can either specify a 0-degree angle, that is the earthquake is in the longitudinal direction of the bridge, or the earthquake is in the perpendicular direction of the bridge. For that we need to specify the angle as 90 degree, and we can specify any angle because the earthquake can be in any direction. So basically the users specify a lot of angles and they try to visualize what results are the worst in what horizontal angles. Then let's talk about the dynamic nodal forces. The dynamic nodal forces are the ones which can be activated and deactivated at certain point of time. And the dynamic nodal load implies that the value of the nodal load can be varied in the due course of time. I will show you how we can do that in the program by making a demonstration. And finally, we can do the time history analysis for the time varying static load too. Sometimes we need to do the time history analysis combining only the self-weight of the structure and the earthquake, and this becomes very useful. Also, the barrier loadings can be simulated with the help of this function. But doing the time varying static load is a little bit tricky process. Why is it tricky? Because we need to combine the earthquake loading with the static loading. So the steps I have summarized here. First, we need to define the self-weight using a time forcing function. Then we will assign the time history load case for the self-weight. Then we will define a time history load case again for the seismic load, and we will make the time history load case for the dead load, that is the self-weight, to be subsequent to the earthquake. So what is happening is the initial time zero for the earthquake loading will be the time when the self-weight is acting. And finally, we can perform the multiple support excitation time history analysis in MIDAS Civil. What it means is, let's say we have piers in the cable stayed bridge which are very far apart. So the earthquake will reach the second pier in due course of time. So basically, the first pier will experience an earthquake much prior to the second pier, and we can simulate that behavior in MIDAS Civil. So now let me take you to the program, and we will simultaneously perform boundary nonlinear analysis, then we'll perform inelastic time history analysis, and then we'll go for the several other options as I told you, multiple support excitation and the dynamic nodal loads. So this is the structure on which I want to do the boundary nonlinear analysis. So first I have defined the lead rubber bearing isolator. Now I am ready to define the time history analysis load cases. I will use the nonlinear analysis time, and the end time I'm using is 50 seconds. And I have selected the damping method to be modal with the same mode damping ratio to all of the modes. The time forcing function, as I told you before, is the earthquake. We can select the earthquake from the database of MIDAS Civil. And after doing this, I need to combine the load cases with the earthquake. So I have selected the load case to be boundary, and I have assigned it an earthquake in the X direction with the horizontal angle of 0 degrees, and I click on add. So my time history definition is complete for the boundary nonlinear analysis. So basically the first step was to define the isolator. The second step was to define the time history load case. The third step was to define the earthquake, that is a time forcing function, and the last step was to assign the earthquake to the time history load case. So now let me open a previously analyzed model, and we will talk in detail about the various analysis results that MIDAS Civil provides for the boundary nonlinear analysis. So here I have specified two load cases. The first is the dead load case, as I told you before, and now I have made the dead load to be subsequent to the earthquake load case, and the earthquake load case is in conjunction with the boundary nonlinear analysis. I have specified the general links at 8 different positions, as you can visualize here, and they separate the structure from the ground support. So now let's talk about the results. The user can see the results for the earthquake at several steps. He can also animate it. The animation gives a clear picture of how the bridge will vibrate or behave for different periods. So as you can see here, this is the behavior of the bridge. And here you can specify the behavior. You can see the displacement, the velocity, or the acceleration. And the several components in terms of dx, dy, dz, and combination of dx, dy, dz, or all of them can be seen at one platform. So the recording has completed, as you can see here, and we can visualize the recording in any format as you want. Now let's talk about the other time history results. We can see the beam, truss, or general link results in terms of the moments, or we can see the shear force, etc. Also, you can make a time history. You can make a function for the output of the time history analysis result in the form of the displacement velocity, or the maximum displacement, maximum acceleration, or the shear. So as you can see here, I have specified a function. Let's say I want to see the deflection of this node. I will say 12th node. I want to see the deflection for earthquake loading. So I can generate the graph for the same. So first I will select the graph which I want to generate. Let's say I want to see the deflection of this node, and I can select the horizontal axis to be time, and once I click on graph, MIDAS Civil will make a graph for me showing the displacement of this node as per time. So this is the displacement of node number 12, which is on the deck as per time. The user can zoom in or zoom out as desired. So this is the boundary nonlinear analysis performed by MIDAS Civil. Now let's talk about the inelastic time history analysis. For performing the inelastic time history analysis, first we need to define the hinges. So the hinges can be defined in modal properties, inelastic hinge properties. In MIDAS Civil, you can specify the hinges to be of various types, and you can select the PMM interaction as we did in the pushover analysis. I can select the code for the same, and I can select the hysteresis model as any one of those. So this is the hinge that I am going to apply. After I define the hinge property, I will assign the hinge to a particular member. So I go to the inelastic hinges, I'll select the property, I will select the beam where I want to specify. So I've selected the beams, the column, and I'll click on assign. So I've assigned the hinge, the inelastic hinge for the inelastic time history analysis. And now once you perform the time history analysis, the material nonlinear behavior will be taken into account along with the damping isolators. So depending on your structure, it's very simple. You can specify, you can make the hinges for the beams as well as you can make the hinges for the columns. But the limitation is that you cannot make the hinges for the plates or the wall elements. So the bottom line is, if you have a beam element model, then you can specify the hinges and you can perform the nonlinear time history analysis, and the results are shown at the same place. If you specify the hinges, then this will be activated and you can see the hinge status as per the step. Now I would talk about the elastic time history analysis, and I will try to show you some other things we didn't talk about yet. So let's say I want to specify multiple support excitation because this bridge has two piers. So I want to specify the earthquake which will appear on this pier at 0 second and this pier at 5th second. So let's see how we can do that. So first I define a time history load case. And I select the analysis type, the damping, and the end time as 20 seconds. Now I'll define the time forcing function, which is an earthquake basically, and I can specify the earthquake. And now I will use the multiple support excitation. So I will specify the earthquake to these nodes at time 0 and to these nodes at time 5 seconds. And now, since as you can see here, I have specified the multiple support excitation. And after I run the analysis, since the structure is a little bit big structure, it contains a lot of elements and cables, it takes 20 seconds. Now I can see the time history results pertaining to the multiple support excitation. So as you can see here, this support is excited by the earthquake and it moves in the direction as you can see here, while this is stagnant, and after 5 seconds the other support has started moving as you can see here. So here as you can see, the first support is excited and it moves, and now the second support is excited after 6 seconds, and this is the earthquake. Now I can specify the dynamic nodal load. So the dynamic nodal load, let's say I want to simulate the moving load analysis for time history analysis, then I can specify the vehicle load at the specific points, and I can add either a sinusoidal function where I can specify the values as how the force varies with time, so I can specify the sinusoidal function, and I can assign or I can specify the nodal load function, So this is the load I want to specify. And after I specify the load, I can select the node and click on apply. And after click on apply, I will be able to assign the load. And after I specify the nodal loads, I can assign that nodal load, I can attach it to an earthquake time forcing function, and I can perform the analysis. So basically the process remains the same as we discussed about the dead loads. First you define the time history analysis for a dead load, then you combine it with an earthquake. The last thing that I'm remaining with is the time varying static forces. So here, as I told you before, you can specify the function for the time varying static load, and you can specify the arrival time, and you can perform the time history analysis with this function. So this was about the dynamic analysis in MIDAS Civil, and I hope I tried to cover everything and you enjoyed the session and learned a lot about it. And if you have any questions now, then you can ask the questions through the chat window available.